All right, a problem with a spring. We have a 5 kilogram mass attached to a spring with spring constant 200 newtons per meter. They lie on a horizontal frictionless surface. Mass pushed against the spring, it compresses the spring by 25 centimeters. Mass is then released. How fast will the mass be moving when it is moving through the equilibrium position? All right, so we have mass, we have spring constant. I'm going to draw a representation of this. Now, when we talk about work done by a spring, we have our equation, negative 1/2 ks final squared plus 1/2 ks initial squared. So we need to talk about two specific moments in time. The moments I would choose is we know we're pushing the mass against the spring so that the spring compresses by 25 centimeters. So what I'm going to do in my picture, I'm going to draw what I mean by equilibrium. And the reason why is the S. Remember, S in this equation means delta S, means how far the spring is stretched or compressed specifically from equilibrium. So I always draw my equilibrium in, and I'm going to draw this initial moment in time. We have this mass, we've compressed it against the spring such that the spring is compressed by 25 centimeters. Then we let it go. As soon as we let it go, we know the spring is going to push the mass. So I essentially could say my final moment in time is going to be the moment the question is specifically asking for. So the mass is released. It wants to know how fast will the mass be moving when it is moving through the equilibrium position. So we're going to say the mass is here moving, but the spring itself is at its equilibrium position. So essentially this second picture, if the mass was not moving, would be when the system was at rest. But because the spring has been pushing on it, it's accelerating the mass. So as it moves through equilibrium, the speed is there. And it's going to be the fastest the mass will go. So we can say initially, S initial is 25 centimeters. S final is 0 because of this moment in time being as we pass through equilibrium. Okay. To relate this to the speed, we want to go ahead and say the net work done on this system is equal to the change in kinetic energy of the system. So 1/2 mv final squared is the final kinetic energy, and then minus the initial kinetic energy. Now, as this mass moves, it of course has the force of the spring acting on it. So force of the spring, there's a normal force up, force of gravity down. So when we say net work, we mean the work done by every single force. So work done by every single force acting on the object, this block in general, as it slides. But remember, because the normal force and the force of gravity both are perpendicular to the displacement, neither one of these will be doing work. And so in this case, the work done by the spring is the net work done. So just as a reminder, they tell us it is a frictionless surface. If there was friction, the net work would be the work done by the spring plus the work done by friction. And that work done by friction, of course, would be negative because it would always be opposing the motion, working to slow the block down. But in this case, we do not have friction, so the only work done is the work done by the spring. So I'm going to put this equation for the work done by the spring in for net work. Okay, so initially, we know the initial compression. We know initial position. Position's not the right word, just initial compression of the spring. We know finally, at this final moment in time, as the mass is moving through equilibrium, the spring at that exact moment is not stretched or compressed. And so that S final term will be gone. In terms of kinetic energy, the speeds, while we push the mass to the side and we release it, we don't give it any sort of initial speed. So we can say that that initial kinetic energy is zero. But of course, the final kinetic energy is not zero because we're trying to find out how fast it's moving. The mass is moving as it passes through equilibrium. But look how nicely this simplifies. That work done by the spring, relating it to kinetic energy. So we're technically relating the force of the spring to speed, but we've already done the integration to calculate the work done by the spring. We don't have to recalculate, reintegrate to find this work done by the spring equation, which is nice. So to finish solving, the 1/2 will cancel. The final will be the square root of K over M, S initial squared, which of course we can pull the S initial squared out if we would like. Sorry, just trying to write that better. So K, they give us 200 newtons per meter. Mass is already in kilograms. S initial 25 centimeters. We do want SI units. We want this to be in meters. And then it is squared if I still have it under the radical sign, the square root. So square root. Getting 1.581. Let's see, 2 sig figs, so 1.6. The units will be meters per second, but I would like to show you why quickly. So under this square root, K is newtons per meter, but a newton is a kilogram meter per second squared. So that cancels with the meters in the denominator. So we can technically write spring constant with units of kilograms per second squared. So kilograms per second squared. The mass is in kilograms, so that's in the denominator, times our delta S is in meters, which needs to be squared. Those kilograms cancel, so that leaves us with meters squared over second squared, but that's all under the square root. And so that's where our meters per second comes from. So you can always follow your units based off of the units on the numbers you're plugging in. And it's a really good idea to make sure your units are working out You don't have to follow them through the whole problem. That's not a problem. But it is very common to mistake some of the units in here somewhere. So we just want to be careful where that's concerned.